everybody. Thanks for tuning back in with WyoTech on how to boost your vehicle. My name's Roger Ogden.
My name's Eric Paul, and today we're going to talk about turbochargers.
So when it comes to boosting your vehicle, there's a multitude of ways to actually do that. Whether it be a supercharger, which you've got typically 3 different types. You've got centrifugals, you've got root, and then you also have a screw type. Today, mainly, we are going to focus on turbochargers because that's what we applied to our vehicle, and that's how we're going to be increasing the boost pressure today.
All right, so as Roger's mentioned in previous episodes, when we're looking at why we would want to put a turbo on engine, a lot of that is just because we want to make more power. Maybe this is a tow vehicle. Maybe we need that additional power. And as he mentioned before, there's also other things that we have to take into consideration, that being, do we have the right fuel system? Do we have the right plumbing? I mean, there's a multitude of different things that go into figuring out why we want a turbo. But more importantly is, what is your main goal? What are you trying to achieve by adding a turbo? Is it you want to make your car faster, or you want to be able to pull your boat to the lake better? Either way, you're going to increase the horsepower of your engine. So Roger, one of the most common questions I get from students all the time is, how do I know which turbo to get?
I mean, honestly, your options are endless, but one of the biggest deciding factors when you're doing this is going to end up being your peak horsepower goal. And you kind of have to stipulate it from there and figure out what you want to sacrifice, because you're always going to sacrifice a little bit of something. One of the biggest things is going to determine our peak horsepower is going to be the outside diameter of this compressor wheel, or when you look on the inside of the housing, it's going to be the inside diameter of the actual compressor housing itself. Going off of that, the inlet is a part that we call the inducer. And when you're actually talking the inducer, that is where the air is drawn in through the front of the turbo, normally where your air filter would be attached, something along those lines. Then it's going to get pulled through, technically compressed, and then it's going to come out of what we call the exducer, which is going to be the outlet of the turbo, or the compressor wheel. The exducer then feeds it out, and it's going to go into the charge pipe, which is then going to deliver it to either the throttle body of your engine, carburetor, or into an intercooler so that you can cool that air. All right, so now we kind of understand the compressor wheel, but what actually drives the compressor wheel, Eric?
So when we're looking at this center housing of this turbo, we've got what we call a turbine wheel. The turbine wheel kind of works the opposite of what Roger was talking about with the compressor wheel. So instead of air, or in this case exhaust, entering the small part of the wheel first, it's going to enter the large part of the wheel first. So our inducer is opposite of what Roger talked about on the compressor wheel. So the larger part of this wheel is our inducer, the smaller part of that wheel is our exducer. What causes this to spin, if you look at this turbo here, we have an inlet. So exhaust is entered through this port. It causes this wheel to spin by the expansion of the heat of gases in the exhaust stream, and it exits out of the backside of the vehicle.
So, as well as having different turbine selections, the other thing we have to consider as well is that the actual turbine housings on these can actually be changed out, and they have the ability to compress the exhaust gas as it's hitting the turbine at different rates. So, like the housing that we have here is a 1.0 on the aspect ratio, which is a cross section. If you were to actually take this exhaust housing and you were to go from the center of the turbine to the center of the area down here, and you divide that by the actual area inside of the exhaust port itself, it gives you what we call an aspect ratio. There's formulas that you can use to calculate that, but for today's video, that's probably going to be a little bit too much in depth. Our biggest thing that we want to hit on is that for this one turbo, you can get generally about 3 to 4 different types of aspect ratios, everywhere down from a 0.9, which is going to compress it more, where you can go all the way up to a 1.2, and they even have a couple like 1.3 aspect ratio housings, which the larger the number, typically the more peak horsepower it's going to support and the less of a restriction that that housing is going to cause.
So Roger had talked about, different housings that we're going to run into, and as far as the aspect ratios, when you start to get into the higher horsepower numbers, what you're going to come up with is when you start to get RPMs up really high, you're going to spin this turbo several thousand RPMs, if not 6-digit RPMs. That being said, we got to be able to support that with good enough bearings. So with not just the plumbing that would go to your intake manifold or the plumbing that would actually go to your exhaust stream, You still got plumbing because you got to supply oil to this guy. Now there's 3 different types of bearings that we can work with on these, and we'll talk about one of them that we have right now, which is what is called a Babbitt bearing. So this Babbitt bearing is actually just going to be encased or with a film of oil that is supplied from the engine. Now because it's a Babbitt bearing, these run on engine oil pressure, so they don't need any type of restrictor or any kind of flow monitoring system in it. You're just going to supply it with the engine oil that you would normally use. Now, when you start to step up in your turbo game to better turbos that'll support higher RPMs, you can go to what is called a ball bearing or a ceramic ball bearing. Now, what the ceramic ball bearing does over a standard ball bearing is that it supports more heat and it will last a lot longer. Now, with the ball bearing type turbos, what you're going to run into is that you have to put oil restrictors, which in this housing right here, you can see there's an oil inlet right here. This oil inlet will have a restrictor that's put in there because if you just feed oil into a ball bearing turbo, you're going to drop oil pressure, which could then in turn starve the rest of your engine from adequate oil. So you put a restrictor in there, you feed your oil line to it, and then that just kind of sort of reduces the amount of oil that goes across that ball bearing.
So as Eric's talking about our ball bearings, the other thing we have to consider is when we go to a ball bearing style turbo, there's kind of there's a big benefit, but there's also one bit of a drawback. So one of the big benefits is going to be that with the reduced friction that you have in it, you can actually get increased spool time, which again is when we actually start to create boost pressure. Generally, it's a rule of thumb around 300 RPM, which may not be a big deal, but if somebody's in the drag lane right next to you, that may be the difference on who wins and who loses. One of the biggest drawbacks is going to be the price. This center cartridge right here roughly is about $1,400. When you jump across to a ball bearing, you're talking $2,800 roughly. But also at the same time, this journal bearing, you can buy a rebuild kit from BorgWarner themselves. They're about $110, $120. Ball bearings generally, they are starting to advance in technology, but currently, not many of them are rebuildable, which means that you have to buy a whole new $2,800 core.
All right, Roger, so we talked about the compressor wheel, we talked about the turbine wheel, but the big question is, how do I know what size turbo to buy them?
Well, there's a couple different factors when it comes to turbine selection, turbo sizing, everything like that. Just this right here, this is a BorgWarner S400 center cartridge, which is going to dictate our shaft diameter, and it gives us about somewhere between 7 to 10 different turbine sizes. Those turbine sizes are going to give us all different characteristics because some of them will have a different count of blades, so how large of a scoop of air they actually get every time that rotates, versus you also have mass that you have to consider as well. The heavier this is, the slower it's going to spool up, which if you're fighting traction issues, a larger turbine might actually assist you in that it takes longer to spool up and your horsepower is going to come in at a higher RPM. So you may be able to get off the line before it actually spools the turbo, which is when we actually start to create boost pressure. So Eric, I always hear the thing, how much boost are you running? Realistically, is that the question we should be asking?
No.
I mean, when you look at these turbochargers, let's say all of these were making 15 pounds of boost. Are they all going to make the same power?
Well, you would think, but no.
We kind of jump back to the comment that I made earlier that your biggest restriction when it comes to your peak power is going to be the inlet of your turbochargers. And that is going to be your biggest flow restriction when it comes to actually producing power. So how does the flow vary between these?
So to answer your question, Roger, I'm going to give you a coffee straw and have you run laps around the building. Only breathe into a coffee straw because that's what we'd be dealing with on a 350 Chevy with that little tiny turbo on it.
Yeah, it doesn't sound like a fun time.
No, but if I give you a garden hose and told you to breathe through that, you'd have more air than you'd ever need for it, wouldn't you?
Definitely would be a lot more for what we're trying to do.
Yeah, so as Roger was saying, with the restrictions of air, we want to try and match that the best that we can. You know, the cubic feet of air we can pull through our engine versus the cubic feet of air we can pull in through our turbo inlet.
So Eric, when it comes to cars and everything like that, everything's always bigger is better, right?
That's what to say.
But is it really?
Nope.
So what's kind of the downfall? Why don't we just skip this medium-sized turbo and why don't we just go for the big guy? I mean, we're going to make more power, right?
Right, but You know, are you racing eighth mile? You racing quarter mile? You looking for a whole shot? What are you looking to do with it?
Doing maybe a half mile, flying mile, something like that. That's all gonna vary on what your turbo selection ends up being. But what's kind of some of the drawbacks to going with the big guy?
Well, you're gonna wait a long time before you get boost. You know, if you're racing an eighth of a mile and you picked way too big a turbo for your application, by the time you started making boost, the race is over that you got passed long ago.
So we kind of mentioned this one on our car currently, it's spooling around like 4,800, 5,000 RPM. What kind of spool rate would you expect on that big guy?
Oh my goodness. Well, closer to your top end peak RPM.
You've got a rev limit of 8,800 RPM. I mean, maybe 7,500, 8,000 RPM it might be spooling.
Maybe.
Which may just be a little bit too much for our car.
Might be. But what compression ratio are you running? I mean, we talked about a basic engine theory.
Yeah, drive pressure is going to end up, how much cylinder pressure you have and how much drive pressure is also going to affect how well these turbochargers spool up. So with something larger like that, where we're not going to get into a ton of boost, that may be one that you want to have to consider raising your compression ratio to help spool it. Or you may get into a little bit of the fun side and maybe you have to spray it with some nitrous or something to help get it lit, which that nitrous then will help you get a little bit more cylinder pressure and drive pressure, which then will slowly get you a little bit more boost pressure.
Wait, we're talking nitrous now?
Nitrous is always fun.
Can we go a big shot with that and a great big turbo and make that work too?
Depends on if you want to keep the internals of the engine inside of it or not. So realistically, when it comes to turbo selection, it kind of varies just what do you want? That is the real question. Do you want the full-blown race car? Or do you want the really nice driving street car that's going to spool up quick, but you don't plan to rev it out to the moon? I'm pretty sure we know what we want.
I think we've made our decision.
So now that we have our turbo selected, we're going to jump into the realm of, we're going to start talking about volumetric efficiency. Eric, what kind of volumetric efficiency was the engine running initially?
80 to 85%.
Which is pretty standard. And we also have this other thing that is kind of lacking up here in Laramie, Wyoming. What's that, Eric?
Oh, it's oxygen.
Yeah, oxygen. Us people, we don't like not having it. What about our cars?
Oh, cars are just as bad as we are.
I mean, how much power are we losing with our lack of oxygen up here?
Well, you figure because of elevation, we're at 7220 here in Laramie, Wyoming, and we're at about 21% less oxygen than sea level.
And so utilizing this turbo, our whole goal is to get more air in there. So if we can compress it and actually increase the amount of oxygen going into our engine, what does that mean?
You're saying overfill a cup?
Yeah, I mean, we're going to physically fill it more than what it originally could fill, which is the concept of volumetric efficiency. An engine can only intake so much. A turbocharger says, yeah, right.
Yeah. So more air coming in means more fuel, means more burn, more cycles. In that case, building more heat in the exhaust. More heat in the exhaust spins the turbine in the turbo. The faster that turbine spins, the more air our cold side of the turbo can draw in and force even more back through the engine, and it's just a vicious cycle over and over again. So what this guy is going to do is it's going to allow us to introduce more air into those cylinders well above 100%.
Typically, more air, more fuel equals more bang. That's pretty much the bottom line.
All right, well, Roger, I think that kind of wraps up, the basics on turbos. Obviously, there's a lot more that goes into it, and there's some math people have to do, but...
Well, I think from there, now we can go over and we can kind of start covering a couple more aspects and some fundamentals that we have to hit in order to get this vehicle to work correctly.
So guys, please hit subscribe. Stay tuned to the channel. We'll teach you a little bit more about how to put all these pieces, parts together to make more power in your car.